In this lecture, we're just going to work out a number of problems involving the integration rules. Each of the problems is just going to add a new feature, and we're going to develop our way up using just the standard methods to more and more complex problems. If you follow along and work out the problems with me, hopefully by the end you'll be very comfortable. Try a few on your own. If you have any questions, make sure you talk to us. You can do this. It's just a very mechanical process. Again, it's not a process involving a lot of creative thought. You need to just apply the rules. So once again, these are just the anti-differentiation rules. Notice they're just exactly the same as the differentiation rules. We talked about this before. You can take out a constant. You have the sum rule, difference rule. We're going to look at this next, the integration by parts or the substitution rule. Oh no, this is integration by parts and the substitution rule. We'll look at substitution next. Again, integration by parts is next semester. There is no version of the quotient rule. Again, we have a version of the power rule. Again, this is when the root can't be -1, of course, because you divide by 0. The exponential, sine, and cosine. Okay, so we're just going to apply these rules in a very methodical process, and again, I'd like you to work along with me. So again, we're going to start out with a relatively straightforward problem, and again, subsequently, each subsequent problem will be more involved and introduce a new feature. But we want to get the basics right. So here's our first problem. Evaluate this indefinite integral. Again, the indefinite integral is a key. If you're going to solve the initial value problem, you're going to use the indefinite integral. If you're going to solve the definite integral, you use the indefinite integral. Okay, so the first step is always to make sure you understand what your function is. You want to break it down so that it's powers, sine, cosine, e to the x. I mean, this is what you're looking for. This is really the only things you can integrate. You want to make sure you have everything set up in this basic form. So that's our antiderivative. I mean, this is our given derivative, and we're trying to find the antiderivative, the set of antiderivatives. So f of x, our derivative, is the cosine of x. And again, if we needed to do any simplification, you'll see on later problems, we'll do it here. Do the algebra first. Anticipate what you're going to do with the problem and take care of the algebra first. So again, I'll work this one out with you, and then the next problems you can add more and more features. Okay, so I'm going to be very precise about how we handle these things. Now we're going to look at the indefinite integral. Right, so what we're going to do is, again, this is exactly analogous to how we handle differentiation. Right? In differentiation, it would be f of x equals d dx, right, of the function, and we'd substitute it in here. Well, this is anti-differentiation. So you see, I'm just going to substitute in the rule, the actual definition of the derivative. Now, again, at this stage, look at the crib sheet. What rule applies? Again, I want you to understand there's only one possibility here. So there's no sense, again, I don't need your opinion on this. Just get the work done. You're a machine, you're a technician. Just get it done as quickly as possible. So the only rule that applies, and again, if you haven't looked at it, pause and look at it, is this rule, right? This is the indefinite integral of the cosine is the set generated by sine. So again, this is the notation I like to use because I think it's a little easier than handling the constants. If you want to introduce and use this notation, that's fine. I mean, honestly, everybody does that. That's better. I mean, that's not better, I think, but if you're comfortable with that, that's fine. They mean exactly the same thing. This is a set. All the functions look like sine x plus a constant. This is a set. Again, understand, this is a set. It means sine x plus a constant. You can literally write the set out, right? Sine x plus this constant, sine x with that constant, infinitely many constants, right? Notice they all feature this root or generator function, right? Each element of this set features this function plus a constant. And that's the key, right? They all look the same. Again, it's just notation. Don't get hung up on it. Every person has their own notation. Sometimes people email me or talk to me and see me from Calc 2 and say, my professor uses a different notation. It's everybody has their own notation. It's like your own penmanship. Okay, so they all mean the same thing. If you ever have a question, just look it up or ask the person. And again, what I want to encourage you to do is, you may not want to, of course we're always lazy, myself included, but you can always check your answer here, right? The generator of this set, again, these are all, any form you use, you have a set, is this function. And so we know this is the antiderivative, so if we take the derivative of this function, the generator of the root, we should get back, using the differentiation rules, our original derivative. So you can always check your answer. And always with the indefinite integral, you can check your answer. So again, that's a nice feature to know for the test or for any other work you're going to do. So again, this is the prototype of how we're going to do these problems. And again, each of the problems is just going to develop a new feature. So why don't you look at this one, pause the video, and give it a shot. Follow the same exact steps. And see how it goes. Again, I see it as good technique. Now I'll jump in a minute, but try to do it. Pause and then try to do it. Okay, let me jump in. I always like the idea, as we did with derivatives, differentiation, of taking some time to put the function in the correct form. Again, this typically involves algebra. You'll see next semester you can get into some geometry gimmicks and some trig gimmicks and so forth and so on. Okay, it always is this step. So what you want to do here is, if you look at the rules, they're basically powers, x to a power, sine, cosine, e to the x, throw in constants, add and subtract them together. So this is what you're looking for to clean up any loose ends, to sort out the problem. Okay, so we have the rule. There's nothing really to do here. We've identified the derivative. Now we need to find the set of antiderivatives. So that's the indefinite integral, is the set of antiderivatives. This is the indefinite integral. And so again, it's going to start out in prototype form. It's standard beginning. Now again, if you look at this, there's only one rule that can possibly apply here. Again, if you haven't done this, pause and try it. But there's only one rule that can possibly apply here, the constant rule, right? So you don't want to put a lot of time into this. You want to see that this is very mechanical. So I'm simply going to take the constant out. In this case, the constant is 3. Okay, and again, if you look at this step, which rule applies? There's only one rule. It's inevitable. You don't have any options here, right? It's the set of sine generated by sine. I said generated by sine. Okay, so there's no flexibility in how you do this. Now again, you don't have to write it in my notation. The 3 comes in. Okay, and again, you can write this to look like this is a set. I want to emphasize the indefinite integral is a set. And it has this generator, this root function, right? Notice every element of this set has that same generator, right? Every one. And we can check our answer once again. The generator of this set is this function, this antiderivative, and check that it is an antiderivative, right? So if I take the derivative of our generator or our root function, right, just use the differentiation rules now, right? We take out the 3, derivative of sine is cosine, and we get our original derivative back, right? And that checks. So we know we did it correctly. And that, again, that's good to know on an exam. You can check your answer. I mean, again, I want you to understand that. You can check your answer. So here's another problem. Again, what I'd like you to do is pause the video and try this, right? Try this. If you get stuck, that's fine. We'll work them out. But give it a shot. You learn by trying. So pause the video and give it a shot. Let me come back then. Again, for me, I'm always going to do this. Let's look at the simplification, at the derivative here. Now, it has the right form for me. It's cosine plus, and again, this would be x to the first power, right? So this is the correct form. I can only look, if you look at the rules, I can only deal with sines, cosines, powers, x to the power, and e to the x. I mean, that's essentially all we can do. That's why this is actually very limited in practice. And that's why converting something into, for example, approximating by converting your derivative into a Taylor approximation works. Again, you'll explore that more in Calc 2. But anyhow, this is what I'm looking for. Sines, cosines, powers, e to the x. So this has the correct form. So we'll move on now to the indefinite integral. Right? It's just a formality. I want you to see, I don't need, again, your opinion here. What I want you to do is just apply the rules efficiently. Again, there's only one rule you can apply at this stage, right? The sum rule. It's the only possibility. It's the only possible rule here. Okay? And now we just divide and conquer, right? We have two problems now to work out. And again, later on, we'll do the same thing we did with the derivatives. Just fold the page in half, and you can work them out on the side. But these are straightforward enough. We'll just jump in. Right? So again, if you look at cosine, the antiderivative of cosine is sine, and the set of the indefinite integral is the set of antiderivatives, sine. Okay? If you look at the right side, again, what's the only rule that applies here? Again, don't hedge this. Make sure you're following this. You can do this, and you can be very successful. It's a power rule, right? My power, again, I don't have to write this down, but I should know. My power is 1. People make mistakes because they do 5 steps at once, and they do it in their head, and they're not clear. Again, I'm not against shortcutting a problem, but the more steps you leave out, the higher the probability of failure. That's how I see it. So my power r is 1, and I just literally plug it in here, and I obtain this. And then formally, I can just put these sets together. And again, I want to emphasize they all look exactly the same, right? All the antiderivatives have the same root, the same generator, the same base, the same principle, whatever you want to call it. Right? They all look like this function, right? So the generator is this function, right? This is an antiderivative. All right, and we can check our work. So I just plug in and check the derivative of this, and I just put all the steps in quickly. You can do it, and it meets my original derivative. So I've been successful. Again, I know I don't need to check the answer in the back of the book. I know for a fact. If I take the derivative of the root, the generator, I get the original derivative back. So this is the antiderivative of this function by definition. Now here's another one. Now notice the new feature here is the definite integral, right? That's the new feature we're looking at here. And so this is my function fx. So take a minute, pause the tape, and work out the indefinite integral first. Just ignore the limits of integration here. Just work out the indefinite integral first. And then pause the tape, try it. Again, there's some issues here that, again, give it a shot and try it. Okay, what do we have? Always, always, always I want to look at the function. Now that's my derivative. But notice what I don't like about this is it's not in the correct template. It's not in the correct form. I don't have x to a power here. And again, why is that important? Because the rules aren't set up to handle it this way. I mean, the rules aren't set up to handle it this way. Notice they just give me the domain of the function here. It goes between -2 and -1. But this is what I'm concerned about. This isn't in the correct form. Right? And again, they gave me the domain. So let's look at this. This is the correct form. Notice I need x to a power. And you can say they mean the same thing. Of course they mean the same thing. They're algebraically equivalent. But I need, in order to apply the rules directly, x to the power. So this is an algebraic preliminary step. I'd like to take care of it before I get into the calculus. Everything has to have this form, sine, cosine, or e to dx, right? So again, for me, do the algebra before you jump into the calculus, and I think it makes life easier. Always look to do this. What I find on exams is people have a lot of trouble with integration. I guess maybe, I don't know, I can speculate reasons. But one of the issues is I believe would solve that problem, or solves that problem, is put it in a preliminary form first. Put it in the correct form first, and you'll make life easier for yourself. Again, remember, your objective here is to optimize your test score. I'm confident this helps. Now, do the indefinite integral. If you haven't done it yet and you didn't make this preliminary step, try it now. Okay, so let's see. Okay, I want to start on a clean sheet so I can put in all the steps. So I'm just, again, they all have the same template form. Of course, with the slides, I just cut and paste, right? I just copy the slides over. So I'm going to, from here, just substitute in the rule of the derivative. Okay, now again, when you look at this, understand it's inevitable. There's no flexibility in what you can do here. I have to use the difference rule, right? You have no choice in this matter. So I have now two problems. So I can look at either one, and what rule applies? The power rule, right, on both. The power rule. They're both powers. And that's why I kind of prefer x to the first power instead of just x. I mean, if you just write x, of course, you understand there's a 1 there. But this forces the inevitability, right? It has to work out like this. And again, you're just going to clean it up now. Clean up the algebra. Put the sets together, right? I'm just going to write this as 1/2 x squared. I just prefer that, and the minus 1 out in front. That's just my personal notation. Combine these sets, right? It's a minus minus. And that's what you have. Again, I want to emphasize this, the indefinite integral, is a set. It's not a function. It's a set of antiderivatives, right? And they all have this base, this root, this generator, right? Each of these functions in here look the same. Right? They all look like this generator plus a constant. Right? And we can check our work. And again, give it a shot. Check. You should take the derivative of this. You should get back your original derivative. Right? So this is an antiderivative. So if we take its derivative, again, notice when I'm going to take the derivative, I also want it in this form, right? I also want it in the form of powers. And so again, if you just plop in all the steps, you come down and you get our original derivative. So this is the antiderivative of this function. Okay, so there was a little more to that. Now we have to come back and look at the definite integral part. But all the hard work has been done. So by the evaluation theorem, the definite integral, right? You know it's a definite integral because it has these limits of integration. It's the lower limit of integration and the upper limit of integration. So we know this is the definite integral. We're going to use the evaluation theorem. Notice this is my root, this is my generator, this is an antiderivative of this function. And really, at this point, the work is easy. And this just goes all through Calc 2, Calc 3. It's always going to work like this. I just simply have to evaluate this function at these endpoints, right? So just do it on the side. I mean, you don't have to, of course, but why jam everything up into here? Take your time. Work the problems out on the right. Don't make sure you don't make a dumb algebra mistake, right? Again, it's just purely algebra. Once I compute these quantities, right, I'm just simply going to replace x with -1 and -2. And I just plug these numbers back in and, again, do the algebra. Right? It's pretty straightforward. So this last step isn't even calculus. It's really just algebra. And again, it's a prototype of how we're going to do problems. Okay, here's another. It's a definite integral problem. So again, pause the video and see if you can do this one. Again, try to be efficient with this. Don't waste time. Try to do this very quickly. It's just a formal exercise. Finish your problems and drive on. Okay, so pause the video and give it a shot. let's see then. I'm going to define the function first, in this case the derivative, right? And it looks like this form. That's that. I get that directly from the problem. They're telling me the domain. Okay, so I have everything set up here. And again, I want to emphasize, I'm just going to use this form to notice that it's really minus 2, right? It's a constant times x to the first power. And this is 4 times 1, and 1 is x to the 0 power. Okay? So it has the prototype form I want. A constant times x to the power, constant times x to the power. Again, you could have sine and cosine in e to the x, but it always has to have this form. And I really want to just emphasize that. So we're going to look at the indefinite integral. Right? So here it is. I'm just putting it on the clean sheet again. Okay, give it a shot. If you haven't, give it a try now. Use the rules. And again, don't make a mountain out of this. It should go very quickly. So let's look at it. Hopefully you've tried this. When I look at this now, only one rule applies here, right? I mean, I want you to see this is inevitable. We're not having a discussion over world history or the politics of whatever. This is a very specific process. We're not here to think. This is just plugging and chugging. So I'm going to use the sum rule, right? And now I broke this into 2 problems. So you can pick this problem, whatever. What do you want to do about that? I'm going to use the constant rule on both of them. I don't really like working two of the problems at the same time, but okay, let's save a little time here. I'm going to take this constant out in front and the constant 4 out in front, right? In this case, the constant's minus 2. In this case, the constant's 4. So at this point, what am I going to do? There's only one rule that applies here, and that's the power rule, right? It's the power rule. So you don't really have any choice. And again, you're welcome to use this notation. In the class, I talk a little more about what this means and how this works, okay? But I just find that people have problems with the constant here and the constant here, and what do you do with it? Well, I mean, you have to think about what it means and so forth and so on, and exactly how you write it out. So this notation avoids that mess with the constants. Okay, so anyway, I'm just going to simplify things. And then I'm going to just bring the constants inside, right? Constants inside, and just clean it all up, right? Clean it all up. And that's it. So again, this means the same. This is a set. This is the generator of that set, right? We're going to check this now. Okay, so if you take the derivative of your generator, you should get back your original derivative, right? This is the antiderivative here, so check that. Right? Let's check. So this is my generator, right? Again, I'm just going to put it in this form. For this problem, it's probably overkill, right? And then you use the same rules backwards. Notice the similarities. I'm using the sum rule, power rule, algebra. Right? There's clearly a link between the differentiation and the anti-differentiation. And so it checks out, right? This is my original derivative. This is the anti-derivative. So, but now we had a definite integral problem. So pause and try that. So the tool we're using, again, is the evaluation theorem to solve these problems. And again, this is predicated upon the fact that you actually have an antiderivative, which in practice doesn't happen very often, but it doesn't matter for these problems. That's my antiderivative. I'm just going to evaluate it at 5 and at 2, right? Purely algebraic steps at this point. Take these numbers and just substitute them back in, and you're done. Here's another problem. So again, pause, give this one a shot, see how it goes. This is actually very similar to the last one, but make sure you try. And again, be efficient about this. See if you can do this quickly, follow the steps, see that it's inevitable. Okay, let's see what we have here. That's my function I'm talking about. Yes, it's a derivative. We're doing anti-differentiation. This is the derivative. And again, they tell us the domain. That's fine. I mean, it's fine. Now, let's see. This is really in this form, right? X to the second power, x to the first power, x to the 0 power. Again, I'm looking for constant times x to the power, constant sine, constant cosine, sine e to the x. This is really what we're looking for. These are our building block functions. So if we solve the indefinite integral, again, I'm just cleaning the page here so it works a little better. So jump in. If you haven't done this, it should be formal. Just apply the rules and do it quickly. Okay, let's look at it. I'm going to use the sum rule. Now you could keep the minus out in front here. That's fine. But minus 2 is a constant anyway, right? So minus 2 is just a number, just the same as 2. So again, if you wanted to put the minus sign here and just have a 2 there, it's the same thing. It means exactly the same thing. And now everything is set up so that we can use the constant rule, right? The constant rule. Take out the 3, take out the minus 2. Either way you'd have it. This is, of course, going to be a minus 2, right? And now we have it as what? The power rule here, right? There's no choice. The power rule. And again, you're welcome to write it in this notation, add a plus c at the end. I mean, it's fine as well. I just feel people get hung up on that, so I'm trying to avoid that. And then you just clean up the algebra, right? The power is 2, 1, 0. So I'm just cleaning up the algebra. I'll bring the constants back inside, right? And then I'll put these sets together. I'm still cleaning up the algebra, right? Put these sets together. So again, you see the powers, cubed, squared, x to the first power, and that's my generator, my root, my principal function. Okay, so, okay, we have this. Now the next step is to check. Take the derivative of this and see if we get back our original function, right? And of course, in this case, you can do it in your head, but I just want to emphasize that you can do that. Again, this is a set, and I don't want you to ever forget that. The indefinite integral is a set. Eventually, I'll stop writing it, but I'm going to nag you until you realize the indefinite integral is a set, right? And that's your generator. Again, it appears everywhere. So we want to check. The generator is this particular function. And if we take its derivative, and again, in this case, you can do it in your head. I'm just, I'll put in the steps. I want to always emphasize it is a process. Even if you're shortcutting it and leaving out the steps, you should be aware. You are applying the rules as we've always done. And that's how it's done. Again, when you get stuck, the reason is maybe you're leaving out too many steps. Go back to basics, right? I mean, you want to train yourself on the more basic problems, right? So you develop a good technique when we get to the more challenging problems. Like that's the issue when we start doing substitution. If you have a good technique, that will be easier. And now we're going to do the evaluation theorem. So again, try it. If you haven't done it already, try it. Okay. So by the evaluation theorem, this is true. Again, the hang up here is finding the antiderivative. Finding any antiderivative. It's difficult in general. In fact, generally you can't find one. But okay, for these problems, they're homework problems in a calculus class, so of course you can. Again, in general, you can. But that's my function. This is my generator. I just evaluated it at 2 endpoints, right? And substituted in. I mean, all the work is in the indefinite integral. I mean, and again, if you set it up in the proper form, hopefully that won't be a problem for you. But yes, there is a lot of work there. Okay, now again, here's another problem. It's getting, they just all have slight variations. So pause the video and give this one a try. Go all the way through to the end if you can, and try to do it again quickly. It shouldn't be thought. It should be very mechanical is what I'm suggesting. Once again, I'm going to just look at the function, right? In this case, the function is the derivative, but that's fine. We're doing anti-differentiation. Once again, they tell me the domain I'm interested in. And again, there's no real simplification. 1 is x to the 0 power, right? And that's how we're going to integrate it, right? So I have powers of x, sine, okay, there's no cosine e to the x, but that's what I'm looking for. That's really all I can integrate straightforward in a straightforward manner. So the indefinite integral, right? Let's set it up. I'm just going to replace fx by its definition. And again, it's inevitable. What's the only rule that applies to this? The only rule that applies here is the sum rule, right? There's no flexibility in this whatsoever. You look at the crib sheet or any set of rules you have in the jacket of the book, and this is how it's done. I mean, this is the only rule that applies. You have no flexibility here. Now, if you look at x to the 0, what's the only rule that applies here? The power rule. There's simply no other choice. Of course, you could use different notation, but it doesn't matter. You have to come up with this. If you look at sine, there's only one rule, right? The antiderivative of sine is minus cosine, right? And now it's just a matter of cleaning the sets up, putting them together in this formal manner. And once again, that's my generator. Okay, and this is a set, and that's my generator. Right, so we want to check this. So I'm not going to write out that this is a set anymore. Hopefully it sank in. The indefinite integral is a set. They all look like this generator plus some constant. So if I take the derivative of this in a way to check, I should get back my original function. Right, so let's check. The generator of this set is this particular function. We take its derivative, right, and just use the standard rules of differentiation, and we should get back our derivative, right? This is the antiderivative of this function is what this says. So by definition, this checks out. Now we can go and apply the evaluation theorem. So the definite integral is, well, the antiderivative, the generator evaluated at the endpoints. So here's our generator. We evaluate it at the endpoints, right? And we just plug in. Okay, so again, this should be very mechanical, I'm hoping. If you're working these out with me, I hope this is very mechanical. Okay, here's another one. Again, give it a shot. They all have some little features to them. Pause the video, give it a shot, try to work these out with me, and you'll be fine. Try a few afterwards. In the class, of course, you'll work them out in the lab to try more, practice some at home, and I mean, you should be good. It shouldn't take 20 hours of effort to do this. Okay, once again, I'm going to look at my function. In this case, of course, it's the derivative. And again, I don't like this form. It's not, the rules of integration are not set up to handle this. Of course, algebraically, it's equivalent to this form, but this is set up as x to the power, right? X to the power. So this is preferable to this form. And again, it's purely an algebraic step, and I suggest you do this in this pre-processing step, right? This is just setting things up so you can apply the integration rules in the next step. Right, so we're going to look at the indefinite integral now. Right, and at this point you should just be formally applying the rules, right? Just in form. Look at the rules and just apply them. Again, if you haven't done it, pause and give it a shot. So again, when you look at this, there's only one rule that you can use here. The difference rule. Right? Only one possibility. If you look at this now, there's only one possible rule that applies, right? The constant rule. Now, if you look at this term or this term, again, there's only one possible rule that applies, the power rule. In this case, the power is -2. In this case, the power is 0. I literally just cut and paste them over here. I mean, that's why I get the typos in the slides sometimes. I just literally cut and paste them, right? And I fail to see one of them or something like that, okay? So I just literally plug these in, and then you're just cleaning it up. Just doing the algebra, right? Just doing the algebra. I'm taking the constant back in, the -1 in front, and I'm combining these sets. And again, this is a set, and that's my generator. This is a set of infinitely many functions. They all look like this principal one, plus some constant. And again, there are infinitely many in here. And I want to check my work. This is an antiderivative, presumably, of this function. So how do I check that? The derivative of this function needs to be this function. And if it is, by definition, it's the antiderivative. So the generator of this set is this particular function. If I take its derivative, again, notice I want to put it in the correct form. We did this with differentiation. I don't really want to use the quotient rule on this. So put it in the correct form, right? It's in the form of powers. Again, you're doing the same kind of things when you're doing anti-differentiation as you are when you're doing differentiation. So I take its derivative, and I'll put the steps in. It's going to work exactly the same way. And of course, there's a similarity between these rules, known as the difference rule, power rule, algebra. But it checks. This function is by definition the antiderivative of our given function. Now we'll go on to evaluate the limits via the evaluation theorem. Right? So pause and try that. Right? The evaluation theorem. Again, it's very easy. All the work is in the indefinite integral step. And that's going to go through Calc 2 and Calc 3. All your work is in the indefinite integral. Finding the generator is finding a particular any antiderivative is in general very difficult. And for, as I said, for general problems, impossible. Well, again, no, I'm not saying you can't integrate it. What I'm saying is you can integrate it by the evaluation theorem, right? You can always, if it's continuous and bounded on the interval, we had a theorem that said it has an integral, it has a definite integral. You can always get that definite integral by the Riemann sums or by the tangent line approach we talked about, the Newton's approach. What I'm saying is it's not possible for most functions to evaluate this by finding an antiderivative. In general, the antiderivative theoretically exists, but you can't write down a formula for it. So I'm just going to plug in. Okay, and it's very straightforward at this point. Now here's another one. Notice this is starting to really get features in here. So I really want you to try this one because again, it looks straightforward, and if you've learned the lessons and you're doing it correctly, you'll have no trouble with this. But jump in regardless. If you have a problem at this, there's something you need to learn. So again, pause the video, give it a shot. Okay, let's look at this. And this is why I really like this preliminary step for problems like this. Again, you could argue for the very easiest problems, this isn't an issue. Maybe that's true, but for problems like this, I see people struggle with this kind of thing on exams. You shouldn't, right? So I'm just going to use the property of square root of top over to square root of bottom. Now remember, square root of 2 is just a number. It's a constant, right? It's just a number. And again, we can't really apply the rules to the square root sign. It's better to write it as a power. And I don't really want the power in the bottom. I want it to look like constants times x to the power. And that's what I've done here. And again, if you're looking for this, it's not a gimmick, it's not a trick, it's not something special. If you're looking for it, you take care of it. And this is the appropriate form now in which to apply the integration rules. So let's look at that, the indefinite integral. So try it on this. Now again, if you didn't notice this in the beginning, learn. Next time, don't be tricked by this. It's just good technique. So look at this and give it a shot if you haven't done it already. So when you look at this, there's only one option here, right? This is a constant. I'm going to take this out using a constant rule. Again, don't be intimidated by the fact that there's a square root here. Who cares? It's just a number. Now, when I look at this, again, there's only one possible rule I can apply here, right? The power rule, and the power is minus 1/2. I like to write it out like this because what I find students do is you make algebra mistakes when you do this in your head. And you confuse differentiation with integration, so you'll subtract here. I like to write it out, and I would encourage you to do so. Again, shortcuts aren't necessarily bad, but again, understand you're training yourself here essentially to take the exam. Do you want to make one of these dumb algebra mistakes on the exam that's going to wind up costing you a couple of points? So again, pay attention. I'm not trying to just nag you. I'm trying to minimize the probability of mistakes. So again, one of the mistakes I see is people who do algebra mistakes here. Be careful. If you've done one already, you know what I'm saying. Just clean it up. Right? Just clean up the algebra, flip this over, bring the square root of 2 in, and that's my generator. So again, this is should be the antiderivative of this function, and you'll know that for a fact when you check your work, right? So the derivative of this function should be this function, and then by definition, this is an antiderivative. So this is my generator. Take its derivative. Again, you could probably do this in your head, but that's whatever. That's fine. I just want you to be aware that we're just going to follow the rules, take out the constant, use the power rule, and so forth. Again, notice there's this similarity between the rules. It's the same power rule, constant rule, so forth and so on. So I know by definition that this function is the antiderivative of our given function. All right? And so next we want to do the evaluation theorem. So if you haven't tried it, pause, give it a shot. Okay, let's look at this. So again, the evaluation theorem tells us that this is what we have, where this is our antiderivative. It works for any antiderivative. We're just going to use the generator. All right, I just evaluated at the endpoints, and I plug it in. And that doesn't really clean up in any way, you know. It doesn't really clean up. Okay, let's just keep working out problems. Now, this is the kind of problem, again, I'm just saying, on exams I see people make a mess of, okay? They'll jump in with every kind of crazy technique in the world. You're trying to do substitution, integration by parts. It's just crazy. Just try it. Set it up using the basic techniques, and you'll see there's no surprises here, okay? Give it a shot. Good luck with this. Give it a shot. Okay, let me jump in. Again, this is why I like this preliminary step. Now, this is not suitable for anything. We're looking for basically powers, x to a power, sine, cosine, e to the x. Clearly, there's no sine, cosine, e to the x here. So we're looking for constant times x to a power, constant x plus or minus constant x to a power. First of all, I noticed that, again, the square root here doesn't help. And I'm just going to do the algebra on the side. Again, you don't have to do everything all at once. I'm going to write square root of x is x to the 1/2 power. And then I'm going to use the distributed property. So it's going to be 2 times x to the 1/2 power minus x to the x to the 1/2 power. Now, I prefer x to the first power because we're going to have to combine these using the algebraic rules. And again, I gave you a list of rules on that crib sheet. And if you're still struggling with algebra, again, jump in, find the rules, right? You're always doing the similar types of algebra. Make sure you're comfortable with it. Don't, like I said, don't ignore it and just say I made one dumb mistake once, because you're going to make that mistake on the final. So I see now I have it in the appropriate form, right? I have a constant times x to the power, a constant, and minus sign is really a constant minus 1, x to the power, right? And this is what I'm looking for. This is the better technique. This is set up now to do the calculus. So again, if you're struggling with problems like this, technique, I cannot overemphasize. Develop good technique, and you'll find that it makes you very efficient in solving these problems. So this has nothing to do with the calculus whatsoever. And again, this is a problem that I see a lot of people struggle with on an exam. And again, you need to do the basics first. So now work on the indefinite integral. I'll give you a moment to try it, or I'll say pause the tape and try it and see how it goes. Okay, let's look at it. When you look at this, you have no flexibility whatsoever. It's going to be the difference rule, right? No flexibility whatsoever. If you look at this term, you have no choice, right? You're going to take out the 2, constant rule. You have no choice. When you look at this term or this term, you have no choice at all. It's the power rule. And now it's just about cleaning up the algebra, right? Just clean up the algebra. And again, I'm going to bring the constant in. I'm going to combine these sets. I'm still cleaning up the algebra. Combine these sets. I personally like constant times x to the power. Again, you can write it differently. I personally prefer this, but it's just my own style. This is therefore my candidate for an antiderivative. Now I know if I take the derivative of this function, I should get this function back. And then I know for a fact I'm correct. So we want to check that. And again, I know you get tired of it, but you're training yourself for the exam, right? Make sure you put this step in. Check that the derivative of this function is our original function, right? Give it a shot. And I put in all the steps here that verify that indeed that's the case, right? So this confirms that this function, our generator, is indeed the antiderivative of this function. Okay, and now we want to apply the evaluation theorem. So I hope you've tried it. If not, pause and give it a try. Right, the evaluation theorem. Again, the evaluation theorem only works if you have an antiderivative. Right, only works if you have an antiderivative. But once I have an antiderivative, yes, it's very nice. Right, it's very nice if you do have an antiderivative because you just plug everything in. So it does make life nice if you have it. Unfortunately, it just doesn't occur very often. Okay. Now here's another one again. I can't overemphasize. You'll have problems like this on the final, and this is straightforward. People tell me, "Oh, I didn't have time to finish it. It took me an hour to work one problem." It's not my fault. If you're not going to follow the steps, it's not my fault. Now again, try it. If you're having any trouble, go back to step 0 and try to put it in the correct form. Okay, let me jump in. This is the form I've been given, but again, I'm looking for x to a power, sine, cosine, e to the x. Clearly, they're not in this, but x to the power. So I'm just going to do algebra, and again, I'm just going to put it in on the right. I'm not saying you have to put all these steps in, but I'm saying this is what it is. I don't like this form. I'm going to just put this, again, use the algebraic rules, so I have x over this, this way. I'm going to combine these powers here, right, and get this. Again, if you look at the algebraic rules on the crib sheet I provided you, or just go to any algebra book and look in the jacket, I guess, you'll see these. Again, on that crib sheet, I wrote down all the rules, the algebraic rules I used for the entirety of this class. And there were only, 20 rules, 20-some rules. And certain rules come up all the time. So again, if you need practice with this, don't hide from it. Jump in, make sure you're comfortable. Because you see, you're doing the same things over and over again. So I like this. X to the power, constant, x to the power, plus minus, constant, x to the power. So this is the form I want to apply the integration rules. So let's work on the indefinite integral at this point. Again, if you haven't done it, pause and jump in. So I'm going to set this up. Again, I want a clean sheet here. And when you look at this now, notice it's inevitable. The only rule I can apply here is the difference rule. Right? The only rule I can apply on this piece is the constant rule. The only rule I can apply on these two is the power rule, right? You don't simply have a choice. It's inevitable. You should look at this as being very technician work. It's not, again, like the last section. The fundamental theorem of calculus. That's brilliant stuff. This, not so much. Right? This is not so much. But this is what's going to be on the test, and this is what people are going to hold you accountable for. In fact, you'll never do this in your anywhere, but okay, this is what you're doing here. Okay, so I'm just cleaning up the algebra. I'm going to bring the 2 in, clean up the algebra, combine these sets to get this generator. Okay, so that's what I have. And once again, that's my generator, or candidate, right? I don't know if I made a mistake. But if I take the derivative of this function, I should get back this function, right? And we need to check that. So again, give it a moment and check it. I know you don't want to do it. No one does. But train yourself for good technique. And it'll work. Again, Calc 2, Calc 3, it's the exact same thing. So I just wrote down all the steps, and I can see that this function now is by definition the antiderivative, a particular antiderivative of this function. And once we have an antiderivative, we can then apply the evaluation theorem. Right? So again, try it. Right? Here we have the antiderivative. We evaluate it at the endpoints, and then we plug in. Okay? Again, you'll see there people have different notation for how to do this. I'm not into 10 ways of doing the same thing, right? I think people really abuse the notation. The most straightforward approach, if you have a different one, fine, but this is what you're doing. Okay, here's another example. And again, these are the kinds of problems that people really make a hash of on the exams. So this is a straightforward problem. If it's not, you're not doing it right. So pause and jump in. Make sure you give this a try. Okay, let's look at this. Again, I'm looking for powers, and of course there's no sine, cosine, or e to the x. Now, I see people jump in on this and they try substitution. Maybe it works, I think it does, but why make it a hard problem? Right? Why make this problem difficult? It's just crazy. You're just asking for trouble. Always do the basics, right? Square it, multiply it all out, and you'll see it's set up as constant x to the powers. Again, you could try substitution. I believe I'm not going to waste time thinking about it, but why not just do the obvious, straightforward, and make the problem easier, right? A little bit of algebra, and I have constant x to the power, constant x to the power. Well, the constant's 1 here, x to the power. This is set up to apply the integration rules in the most basic, straightforward manner. So let's look at that. If you haven't done it, pause and give it a try. Okay. Now, again, it's inevitable what happens here. I'm using the sum rule. I'm going to just consider -4 to be a constant. It is, right? -4 is just as valid as 4. But if you want to make a minus sign here and a 4 here, it's fine. It's style, only style. And now when I look at this term or this term, there's only one possible rule that can apply, right? The constant rule. Again, you have no flexibility here. This, and this now, there's no other way to do it other than the power rule, right? R in this case is 2. R in this case is 1. R in this case is 0. And then we're just going to clean things up, combine the sets, right? Clean things up, combine the sets. And that's going to give me my candidate for my antiderivative. Now again, I know it's an antiderivative for a fact when I check it, but right now I may have made an algebra mistake, so you should check. And again, I just did all the work here, and we see in fact that this is the antiderivative of this function, again, by definition of what an antiderivative is, right? I give you the derivative, you find the antiderivative. And again, notice these are just the standard basic differentiation rules from the first part of the course. Okay, but we want a definite integral, so you need to apply the evaluation theorem. So again, if you haven't done it, try it. It's just going to look like this. And here's our antiderivative, our generator. So just plug in the endpoints, the limits of integration. And again, it's just inevitable. It's just algebra at this point, right? All the work is really the indefinite integral. And that'll continue in Calc 2 and 3. All the work is the indefinite integral. Okay, this is a little trickier, right? Can you do it? You can try and see what happens here. But if you have problems with this, I'll buy it, right? This is a little more extreme. So give it a shot. I mean, really, give it a shot. Force yourself to try this. You'll learn something. Now again, here's my step 0. This, remember, the absolute value is a function. It's a piecewise function, right? So in this step, you need to get to write this as its piecewise form, right? It's a piecewise function, right? A is just a placeholder. Whatever goes in this box, I could call it X, of course, but I don't want you to get confused. Whatever goes in this box goes in this box, this box, this box, and this box. It's just cutting and pasting, right? Maybe this is a better way we should write it these days, right? So you should think of this as whatever goes in the box here gets placed in these boxes here, right? So I have 2x minus 1. Right? Don't be intimidated by this. Now, I don't like to write out this. I like to write x is greater than equal to something or x is less than something. And that's all I'm going to do. You just want to clean this up a little bit, right? This isn't, it doesn't tell me the x I want. So I'm just going to clean this up. If 2x minus 1 is greater than equal to 0, just do the algebra that says x is greater than equal to 1/2. And notice I took the minus sign in through here. Minus 2x minus 1 is plus 1. So it's just, this is a cleaner form of this. So there's a break at 1/2, right? And here's the picture. Here's the picture. So notice there's just a different rule on this piece and this piece. So how are we going to do this? Well, we did have a theorem. I did pass through it quickly. But think about the integral is, remember, these Riemann sums. So we'll just Riemann sum up, square this piece, and then we'll do this piece, 2 separate problems. Sorry, I went too fast. You just break this down into the 2 problems. This piece, right, 0 to 1/2, so you do the sums on this piece using the appropriate rule. And you do then the sums on the second piece using the appropriate rules. And I'm not going to do it. You can finish that off at this point if you like. And the last one I look at is, here's another way of stating the problem. If your function is positive, right, if it's positive, the definite integral can be interpreted as the area. I mean, think about it. You're putting a lot of rectangles under here, right? And what the rectangles are is areas. So this says you're summing up rectangles. You're summing up areas, right? Base times height. So this is interpreted as an area. Now, when you have it positive and negative, you have to start thinking about what it interprets, right? But this is interpreted as the area. Think about it. It's all rectangles under here. That's how you actually calculate this with Riemann sums. Okay, and that's it. So another way of setting up a definite integral problem is saying, determine the area under this curve. And that's it. That's this problem. And again, you just do this the same way we've been doing it. It's now a definite integral problem.